Hello, my name's Jason Lambert, and today we're going to talk about Ohm's law. We will see over the next few minutes how Ohm's law is core to circuit analysis, a small history on the law, and how it can be used. George Ohm, that's him on the left, wrote a book in 1827 that featured Ohm's law. Though coldly received at the time, Ohm's law has grown to become the baseline for any education to do with electricity. Most of you probably learned about Ohm's law in Year 9. However, in his time, even the most educated disregarded his work. The basis of Ohm's law is his equation, V equals IR, alternatively E equals IR, where V or E is voltage in volt, I is current in amperes or amps for short, and R is resistance in ohms. George Ohm was the first to express this relationship, therefore the law is named after him. He noted that there was a direct relationship between voltage in a circuit and current, meaning that as voltage increases, so does current. This can be related mathematically to the linear form of the line, y equals mx, where y is some dependent variable, comparable to v, and x is an independent variable, comparable to I. This shows that the linear relationship of v equals IR is simply voltage equals to current scaled by some value R, in the same way that a straight line is scaled by a gradient m. This idea can be carried over to V equals IR to demonstrate that no matter what the current, voltage will always be directly proportional to the current. That is, as voltage increases, current increases. But of course we're talking electricity here, not water. We see all this and think, how can we use this? Well, firstly, if we know two of the unknowns for any circuit, the third can be calculated using the simple relationship and rearranging the formula. Secondly, for AC circuits with a voltage defined as shown, relationships for both AC current and AC resistance can be easily formulated through Ohm's law. Ohm's law can also be used in nodal analysis, which uses KCL, however is solely based on Ohm's law, the reduction method of solving circuits, whereby a circuit is reduced down to a simple 1 resistor, 1 power supply circuit, also known as base case. Ohm's law is applied there and can be used to find all currents, resistances, and voltages in the entire complex circuit. Just so happens that wherever you look in the field of electronics, the more and more you see Ohm's law pop up. Ohm's law, however, is not all bells and whistles. It has some limitations. For example, Ohm's law assumes that temperature of the material remains constant, thus allowing resistance to remain constant. However, if we consider resistance to vary with temperature, as it does in real life, we see that Ohm's law suddenly becomes much less streamlined. Furthermore, Ohm's law, due to being produced by means typical of the classic model, it finds no usability in the subatomic and quantum level. For simple everyday calculation of circuits on a macroscopic level, Ohm's law works fine, as long as we don't look too close.